Folks, that's fine. I've got the sign-in sheet coming around. I've been asked to pass out these major fair notifications. Majors Fair is next Thursday. And it actually works with our lab system. It's not a dog any other or okay. So today we will be covering ions of the elements. With the ions of the elements, we're going to look at the protons and the number of protons and the number of electrons. We'll also get into the electron configuration. To be able to do that, I'm going to introduce this concept of valence electrons and core electrons, and then we're going to move on to atomic trend, where we'll spend a bit of time on Z effective and shielding, because it is shielding and Z effective that allows us to understand the atomic trends, which includes atomic size, ion size, ionization energy, and electron affinity. So that is the plan for today. So ions. Ions are basically charged atoms of elements. These charges result from an exchange of electrons between one element to the next. For the ions, we have two types. They can either be a cation or an anion. A cation is going to be an element that loses electrons to make a positively charged ion. And with respect to our elements, that means they're going to be metals. So I could rephrase this. It is the result of metals losing electrons to form positively charged ions. The second is the anion. The anion results from the gain of electrons to make negatively charged ions. The elements that will form an anion are going to be your nonmetals and metalloids. So on this past test, you were asked to highlight or to shade in all the nonmetals. Well, and you were asked, who are the metalloids? That division isn't particularly important if you're going to be able to determine who's going to make a cation and who's going to make an anion. Because the metals are going to make cations and the nonmetals and metalloids are going to make anions. Now, in our cations, we have certain elements that always form the same charge. And those elements that always are going to form the same charge include group 1. Your group 1 metals will always form a +1 charge. So lithium, sodium, potassium, it doesn't matter what compound those elements are in, those elements will be in the form of a +1 charge. Your alkaline earth metals will always form a +2 charge. In other words, your group 2 metals will always form a +2 charge. So beryllium, magnesium, calcium, if you find those in compounds, they're going to be in the form of a +2. Now, there are 6 additional elements who always form a specific charge. And those elements, it's a little bit harder to remember because for the first ones, it was group 1, group 2. Group 1 plus 1, group 2 plus 2. But it's a little harder to remember these other 6 simply because of where they are on the periodic table. So over the years, I looked at it long enough that I realized that these elements form a nice staircase on the periodic table. That staircase starts with silver. It goes to zinc and cadmium, and then to aluminum, gallium, and indium. Now, in memorizing the charges that they form, one way you can do that is to understand that it does form this nice, neat staircase. And it just so happens that the charge it forms is equivalent to the number of elements in that particular step. So in silver, there is only one element in that step, and that is silver. It always forms a +1 charge. With cadmium and zinc, there are 2 elements in that step, and they both always form a +2 charge. For aluminum, gallium, and indium, there are 3 elements in that step, and all 3 of them form a 3+ charge. So that is one way to memorize your charges that those particular elements form. And yes, I did use the word memorize. As we get into the electron configurations, hopefully it'll be more understandable as to why they form the elements or the charges that they do, but it is a matter of memory work for most people. Now, all other metals that I have not described here, all other metals can form more than one charge. So at this point in time, I'm going to have to tell you what that charge is. When we start getting into ionic compounds, I'm going to teach you how to determine the charge given the formula. But for now, it's all going to be, I'll have to give you that information. Questions? Now you may ask about the anions and anions. I mean the nonmetals and metalloids forming anions. Group 15. Forms a -3 charge. Group 16 forms a -2 charge. And group 17 forms a -1 charge. We are going to find that the charge that they form is directly related to their electronic structure and how many more electrons a subshell can handle before it is full. Questions so far? Okay. So the electrons responsible for how an element behaves are primarily the valence electrons. The valence electrons are going to be the electrons in the outermost shell. In other words, in the highest principal quantum number. Again, your valence electrons are going to be the electrons in the outermost shell or the highest principal quantum number. All other electrons are the core electrons. So before we move forward, let's talk about how to determine, let's talk about these number of valence electrons. In lithium, its electron configuration is 1s2, 2s1. The highest shell, the highest quantum number is 2. There is 1 electron in that quantum number of 2. So lithium has 1 valence electron. And it is that valence electron that's responsible for its charge, because if you'll recall, if you look back, I said group 1 always forms a +1. Group 1 always forms a +1 because they have 1 valence electrons. Just to illustrate that, let's look at sodium. Sodium has a the highest shell is 3. And just like lithium, there is only 1 electron in that highest shell. So it too has 1 valence electron. Lithium and sodium behave the exact same way, folks, because they have the exact same numbers of valence electrons. Lithium and sodium behave the exact same way because they have the same number of valence electrons. They both form a +1 because they only have 1 valence electron. Now, when you get into the transition metals, the valence electron definition remains the same. It's the highest shell. Well, for iron, the highest shell is 4. And it has 2 valence electrons. So iron has 2 valence electrons. The majority of your transition metals will have 2 valence electrons, because there will be 2 electrons in that S subshell that precedes the D. The majority will have 2 valence electrons. The exception to that rule is group 6 and group 11, which I went over the other day as anomalies. And if you look at silver, for instance, silver's electron configuration of krypton 5s14010, it actually only has 1 valence electron. So when you're talking about the anomalies, they tend to only have one valence electron, but all of the other transition metals typically have two. Now, looking over at chlorine and bromine. Chlorine, its highest shell is 3. There are 2 electrons in the 3s and 5 electrons in the 3p, making a total of 7 valence electrons for chlorine. Bromine, the highest shell is 4. There are 2 electrons in the 4s, and there are 5 electrons in the 4p. So again, bromine has 7 valence electrons. I could have guessed that bromine had 7 valence electrons because all elements in group 17 are going to behave the same way. So if chlorine has 7, bromine's going to have 7, so is iodine. So is fluorine. It is because they have the same number of valence electrons that they behave similarly. So again, your valence electrons are the electrons in the outermost shell, which is the highest energy level. And those are the electrons that are going to be responsible for an element's reactivity. I should say those are the primary electrons responsible for an element's reactivity. If it's not a valence electron, then it's a core electron. Questions about valence and core electrons? Then let's look at electron configurations of ions. So a few moments ago, I gave you lithium as 1s2, 2s1. Lithium is element number 3. So its atomic number is 3, meaning that it has 3 protons and 3 electrons. So we wrote the electron configuration of lithium as 1s2, 2s1. Now, lithium is a metal. Metals lose electrons to make cations. So lithium is going to lose its valence electron, because again, the valence electrons are responsible for an element's reactivity. So its valence electron again is this 2s1. As we move to make lithium ion, it is going to lose that 1 electron to have the electron configuration of 1s2, because that 1 electron is going to go away. As far as its atomic number, protons and electrons, lithium still is going to be atomic number 3. The atomic number cannot change. The number of protons cannot change because the identity is lithium. The only thing allowed to change is the electrons. And we lost 1 electron. So in other words, Li plus has only 2 electrons in it. Take a moment and digest that. Let's talk sodium to give a second example. Sodium is element number 11 on the periodic table. So its atomic number is 11. It'll have 11 protons and it'll have 11 electrons. That is why its electron configuration is 1s2, 2s2, 2p6, 3s2. I mean, excuse me, 3s1. Again, the thing to note, lithium is a metal. I'm sorry, sodium. Sodium is a metal. Metals lose electrons to make cations. Sodium will lose its valence electrons in the formation of the cation. So if we make sodium ion, it's still going to be atomic number 11 because it is still sodium, which means it's still going to have 11 protons. But now it's going to have 10 electrons in sodium ion. And the electron that it has to lose is going to be this valence electron. That valence electron is going to go away so that the electron configuration for sodium ion is 1s2, 2s2, 2p6. Questions about the first two examples? Folks, you may wonder how I know plus and minus as far as the number of electrons and number of protons. Let's just quickly talk about that. First of all, what charge does a proton have? Positive. A proton is a positive 1, and there are 11 of those. What charge does an electron have? Negative, and there are 10 of those. If you add that together, plus 11 minus 10, you get a plus 1, which is the same thing as the charge. Okay, let's get into iron. Again, iron is a metal. Metals lose electrons. To make cations. So in other words, iron will lose its valence electrons, which I'll start doing as VE first. So first of all, iron is element number 26. So that's its atomic number and its number of protons. 26 protons means that there's 26 electrons. So the electron configuration in the noble gas form for iron is going to be argon 4s2 3d6. Again, iron must lose its valence electrons first. So it's going to lose the 4s2 first. Those are going to go away first. To make iron 2 plus, which is still going to have 26 protons and 26, or an atomic number of 26. But now if it's lost 2 electrons, it has to have 24 electrons left. Again, the 2 electrons lost have to be the valence electrons. So iron's electron configuration is argon 3d6, iron 2 plus. Questions? If you cannot identify the valence electrons, you are going to remove the electrons from the wrong location. It is essential you be able to identify the valence electrons so that you remove those first. Now, iron 3 plus means I have to lose 3 electrons. So I'll have 26 protons and an atomic number of 26, but now I'm only going to be allowed 23 electrons. I'm going to go back up to this starting point up here. Again, you lose your valence electrons first. So these electrons will be the first ones to go away. That's 2. But I have to lose a 3rd electron. So I'm going to lose one from that 6th layer, from that 6 as well. And so what results is argon 3d5. Iron forms a +2 and a +3, folks. That's the only 2 charges iron will form. And it does so because to form a +2 means it loses its valence electrons. And to form a +3, well, by forming a +3, if we look at the box diagram, we have a half-filled subshell by losing 3. And what did I say on Tuesday about half-filled subshells? They're more stable. So iron 2 and iron 3 are the only forms of ion that you will encounter. Iron 2 results from the loss of valence electrons. Iron 3 results from the loss of that 3rd electron to make a half-filled subshell, which adds stability. I said up there, up here, silver always formed a +1. Silver is element number 47 on the periodic table. So it has 47, atomic number 47, it has 47 protons, and in a neutral atom, it's going to have 47 electrons. It's going to have the electron configuration of krypton 5s1 4d10. because it is an anomaly. Now, silver, again, is a metal. And metals lose electrons. To form cations. Silver will lose its valence electron first. So silver is going to lose that 5s1 first because 5 is the highest shell. So when we make silver ion, we have 47 protons, but now we have 46 electrons. And the electron configuration is krypton 4d10 because we lost that 5s. It only forms a +1 charge because by losing that 1 electron, what's left is a full subshell. Questions about the cations? Let's deal with our anions. Chlorine is a non-metal. Non-metals gain electrons to form anions. The number gained, or the number of electrons gained, equals the number needed to have the same number of electrons as the nearest noble gas. Chlorine needs to gain 1 electron. It is element number 17. So it has 17 protons and 17 electrons. But if chlorine makes Cl minus, then it'll still have 17 protons, but it gains an electron to make an anion. And by only gaining 1 electron, it's going to have the same number of electrons as argon now. So its electron configuration becomes 1s2, 2s2, 2p6. Oxygen has 8, is atomic number 8, so it has 8 protons and 8 electrons in its neutral form, which is 1s2, 2s2, 2p4. Oxygen is a nonmetal, and nonmetals gain electrons to form anions. The number of electrons gained equals the number of electrons needed to have the same number of electrons as the nearest noble gas. So oxygen forms an O2 minus charge by gaining 2 electrons to have 10 electrons. And if you notice, if it has 10 electrons, it's going to have the same number of electrons as neon. So its electron configuration would be 1s2, 2s2, 2p6. Questions? Okay, so at this point in our study of the atom, we have discussed the number of protons and in the nucleus, and it's the number of protons that determine the identity of the element. We have, using the mass number, been able to generate the number of neutrons also in the nucleus, and the number of neutrons determines the isotope of the element. We then have spent a lot of time talking about the electronic structure, where are the electrons located? And we started our discussion about the electronic structure with the quantum numbers, because it was the science that led to the quantum numbers that ultimately led to our understanding of where every electron in the atom is located. And so we talked about the quantum numbers, and then we got into electron configurations. We've dealt with the electron configurations of neutral atoms. We've dealt with the electron configuration of anomalies. And now we have dealt with the electron configurations of ions. So you should understand where every single subatomic particle resides in the atom of the element at this point, or in an ion of an element at this point. Down to the shape of the orbital it's in. Where we move next is to understand how this electronic structure and the number of protons in the nucleus directly impact some of the atomic trends, such as the size of the atom, such as the size of the ion, such as the ionization energy. And to really understand that, we have to understand two concepts. The first is shielding. if I think about a shield, my mind automatically goes to something like King Arthur, where they have a shield that protects them. Basically, that shield is a barrier. Or, and I can think of other shielding forms like a wall. A wall would shield you from the outside. That is all shielding is with respect to an atom, except shielding is, in this particular case, is associated with the shell. So when you have hydrogen, you have your nucleus, and that electron is right up against the nucleus. There is absolutely no shielding involved. That hydrogen's electron feels everything that's in that nucleus. But as we grow our atoms so that we have a second shell, once you grow your atom to have that second shell, now that first shell provides a wall. It's a wall between the nucleus and these outer electrons. So the shell provides the wall. When you grow it to the third shell, now you've got the first shell and the second shell that is providing a wall between the electron and the nucleus. So these shells, as we add on these shells, what we're doing is we're creating shielding by putting up barriers between the nucleus and the outer electron. The other part of the story is a very important part of the story, and that is the Z effective. Z effective is the effective nuclear charge. Basically, Z effective describes how strongly the nucleus pulls on those outer electrons. In other words, you can think of it as a magnet. If I have a really strong nucleus, a really strong positive magnet, it's going to be taking those electrons and it's going to be pulling it very close to it, which is going to cause a shift in the atomic size. So the other part of the story is Z effective. Now, which of these two factors, the barrier or the Z effective, has the most impact on these trends? The answer is the shielding. Shielding has the greatest impact. Putting up walls has the greatest impact in keeping that electron from finding the nucleus. But right behind it is Z effective. Now, Z effective can be determined using Slater's rules. And I have put up here what Slater's rules are in a tabular format. So you will notice that there's a specific rule for your 1s electrons. So there's a specific rule for those electrons that would be associated with hydrogen and helium, essentially. There is a rule for the S subshell and P subshell electrons. And there is a rule for the D subshell and F subshell electrons. Going across the top of this table, what you're doing is you're describing the impacts that the other electrons have on a specific electron. So we're describing the impact the other electrons have on a specific electron. If they are in the same shell, then unless they're in the 1s, which is 0.3, they're going to be a 0.35 impact. This is just a numerical value that has been determined over time. Now, the further away from the nucleus the electrons reside, again, that shielding effect becomes more and more prominent. And so electrons in a shell with principal quantum number that is equal to the electrons with principal quantum number -1, if it's in an S or P, it's going to have an effect of 0.85, whereas if it's in a D or an F, it's going to automatically have an impact of 1. If there are more than one shell in between, then you're going to get into this column. So, where the principal quantum number is equal to n-2. And you will notice that those have a very significant effect because 1 is the highest we can get. They have a significant effect. So the way to think about it is same shell, one shell in, two shells and more in. Or another way to think of it is this. So our in here is just out here, in. So this is the fourth shell out. Any electron in the fourth shell has a 0.35 impact. In the third shell, that is n-1, every electron in the third shell, in this case, would have an impact of 0.85 if it's an N or an S. I mean, an S or a P. Or it will have a 1 if it's a D or an F. In the second shell in, all of those, no matter what type it is, has a 1. And same thing with the third shell in. So again, that 1s point, that 0.3 is only for helium, really. It doesn't matter for anybody else but helium. Sure. Yes, you can take pictures of any slide you need. If you're concerned, you'll make a mistake in translating. Okay, so to calculate Z effective, it is Z minus S. S is all of this that I've been talking about. Z is your atomic number, or in other words, your number of protons. So S is everything I've been talking about up here, whereas Z is just your atomic number. And we're fixing to put this in action. And I'm doing several problems. And my experience is of the things I've talked about today, this is the toughest. So speak up if you have questions. Speak up if it does not make sense. Because a lot of places don't teach the effective. Okay. Helium is 1s2. Its atomic number is 2. And ultimately, to get our Z effective, it is going to equal our atomic number minus our shielding. So it's going to equal 2 minus our shielding. Now we need to figure out the shielding. Basically, if we think about helium here, what we're dealing with is we have electron 1 and we have electron 2. What I want to know is electron 2. So we're calculating the S for electron 2. Now, according to that table I gave you, for the 1s, it's a 0.3. So in other words, so that's equal to a 0.3 times the 1 electron times 1. Or in other words, it's 0.3. So our Z effective for this is 1.7 for helium. Okay, let me go back and explain now that everybody's written it down. I am trying to figure out the impact on this electron. That's what I'm trying to do. Well, the impact on this electron is related to that electron, which there is only one of them. Because it's in the 1s shell, I multiply it by a 0.3, and that's where that 0.3 comes from for the shielding. So we take our Z, which is our atomic number, and we subtract out that shielding, and we find out that the Z effective for helium is 1.7. I'm going to explain how these numbers impact atomic size and stuff like that on Tuesday, it looks like. Right now, I just want us to get to the calculations of Z effective. Okay, lithium. Oops. Lithium has our nucleus here. It has electrons in the 1s, and it has an electron in the 2s. I want to know what is going on with this electron. So my shielding for that electron is going to equal, well, this is shell 2, this is shell 1. So my N here is equal to 2, because that's the one where I want to figure out what's happening to that electron. Now, going back up, we don't have an electron in the same shell, so it doesn't matter, because there was only one electron in that N2. But we do have an electron in the N-1, because 2 minus 1 is equal to 1. So in the first shell, we have an electron. It is in the NS. And so we're going to take those 2 electrons that are in the NS, and we're going to multiply them by 0.85. And if I'm not mistaken, that comes out to be 1.70. So our Z effective is going to equal 3, because that's our atomic number, minus 1.7, which comes out to be 1.3. Questions? So notice I'm not paying attention to the last electron. I don't pay attention to the 2s1. I'm focused entirely on all the other electrons. Let's look at sodium. Sodium is 1s2, 2s2, 2p6, 3s1. I'm going to figure out what's going to happen to this 3s1. Now, folks, I can actually figure it out for every single electron in the atom by using these rules. I'm just always going to go with the outer one, because that is the one that's going to make the most impact on atomic size and stuff like that, which is where I'm using Z effective the most. So I'm not going to pay attention to that 3s1, because that's the electron I'm studying. This is in the N-1, because it's 3 minus 1, which is equal to 2. And therefore, these 8 electrons are going to be 0.85. Over here, this is in the N-2, because 3 minus 2 is equal to 1. And therefore, these are going to cause a entire one impact. So my S value for that electron that I'm looking at is going to equal 8 times 0.85 plus 2 times 1. And this one I can't do in my head, and I don't have my calculator or my phone with me today. So if somebody can do the math, I'd appreciate it. It came from so I was asked, where did this 8 come from? Whoops, I want to get this one. Where does that 8 come from? It comes from 2 plus 6, because those are both in the 2. Okay. So this comes out to be equal to 8.8. So our Z effective is going to equal 11 minus 8.8, which is 2.2. That is the Z effective on the sodium. Yes. There is no units on this Z effective. If you want to consider it as a unit, it would be the pool, which that doesn't really have a unit between the nucleus positive and that outer electron. So that's what the Z effective is. I guess it would be coulombs, because that's how we usually describe the pool of the electrons. But I don't really worry about a unit on this one, because these aren't exact quantities, they are estimates. Why did I do what? Okay, because so the shielding, basically it's like, so let me skip down to the bottom where I've got space to draw. Yeah. So for sodium, here's your nucleus. And in the first shell, you have 2 electrons. In the second shell, you have 8 of them. And then you have our electron in question that I've been working with in this outermost shell. Okay. Now, the reason I added it is because this electron causes a 0.85. This electron causes a 0.85. This one 0.85. And I can continue. And then these cause a 1. So I added all those numbers up essentially, because because in that table I gave you, that's describing what each and every electron causes on that electron you're evaluating. Does that answer your question in a graphical method? Does that? And if you need to draw it like this, you could draw it like this, just so that you can see the impact and why I did 8 times 8 point, and why I did 8 times 0.85 and 2 times 1. Other questions? The reason we don't care about the one on the outside is because this one is the electron I'm evaluating. And if it's the electron you're evaluating, it isn't going to have an impact upon itself. So this has no impact on itself. And that's why we don't take it into account. Does that answer your question? Okay, let's go back up here to iron. Okay, this is the one place where the full electron configuration is pretty much a must. So iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Now, I am going to evaluate one of these electrons. So I'm starting with N of 4. Well, I'm only evaluating one of those electrons, so there's still one of them in there. So this is going to be 1 times 0.35, according to that table. Now, according to this table, if it's N minus 1 and it's an S or a P, it's 0.85. So these are N minus 1, because that will equal 3. And this is an S and P. So this is going to be 8 times 0.85. And I'll write it out larger in a minute. Now, all of these have a N greater than or, I'm sorry, less than or equal to N minus 2. And they are S and P. So all of these, which is 10 of them, are going to impact it by by 1. That leaves our 3D, which is in the N minus 1, which is 3. Well, if you look back up at the table, and like I said, I'll write it out bigger, N minus 1 for D is a 1. So these 6 are going to be a 1. So what we have for the electron we're evaluating, our S is going to equal 10 times 1 for our first shell and second shell, plus 8 times 0.85 for our third shell S&P, plus 1 times 0.35 for our 4S, plus 6 times 1 for our 3D. So 8.8, and I add another 14, huh? 8.8 and 15 is, yeah, you did it right. 23 point what? 15. So our Z effective is going to equal iron, which is 26, minus that 23.15, or in other words, it's 2.85. Questions?
Would you just like neglect the like electrons that are closest to it? Like
No, even the ones, if you go to the 5th level, so basically, once you get to the 3rd level, those electrons that are closest to the nucleus are going to count 1 against it. So if you go to the 5th level, they're still going to count minus, right. It's in anything that is less than N minus or greater than N minus 2. So in other words, less than N minus 2 actually. Okay, we will pick up with the meaning of all of this on Tuesday. I would highly recommend practicing it. There is homework directly related to it, and I would recommend practicing it, folks.